everyone, and welcome to this month's Python Exchange. Today we have a very special event planned for you because we are joined by Gaël Varoquaux, who is a research director working on data science at the Inria, French Computer Science National Research, where he leads the SODA team. He's also a co-founder and scientific advisor of Probabl. His research covers fundamentals of artificial intelligence, statistical learning, natural language processing, causal inference, and as well, or in addition to, applications to health with a focus on public health and epidemiology. He also creates technology, co-founding scikit-learn, one of the reference machine learning toolboxes in Python, and has helped build various central tools for data analysis in Python. And in fact, he's going to share one of those tools with us today. With that all being said, we're going to turn things immediately over to Gaël. So Gaël, why don't you go ahead and tell us a little bit about what you have prepared for us today, and afterwards we'll jump into a very engaging Q&A where if you're in our audience joining, please feel free to submit your questions via the chat, and we will also invite the rest of our panelists up on board to have a great discussion. But Gaël, I'll turn things over to you.
Hi everyone, thanks a lot, Cameron. So today I want to talk about something that we've been brewing for a little while. It's really been shaping in the last year. We call it Scrub, and I'll get a bit into the details of it. But first, maybe let me tell you how we got there. So, been doing data science, machine learning, AI, you name it, for quite a few years, and with all kind of applications that I've looked at, and in particular, talking to people who work in the industry, who work on a bunch of applications, it seems that, we've solved one problem and there was much, much more to solve. And that much, much more is what I want to talk about today. So, we've done things like scikit-learn, but we've left a lot. And so maybe, I can share my screen. So I'm going to try to do something unusual today. I'm going to try to do a presentation fully in VS Code. This is the first time I do it. I'm probably going to fuck it up, right? So let me share my screen. All right, you should now be seeing a VS Code. And just to start, so as I mentioned, I want to talk about something kind of new. It's been brewing for 1 year. It's called Scrub, and the idea really is to focus on the data preparation, the data wrangling, everything that goes before the machine learning. And I just want to say, so this presentation is just a bunch of Markdown files and of Python files, and they're available on GitHub. You can see the URL here. And so, so machine learning has become really important for data science. And the reason really is that it's how we make the best of data. So we live in a really data intensive era. There are plenty of places that are accumulating data. And, to use this complex data, well, machine learning is really central because the data is complex, and in machine learning is basically very complex statistical estimators. So now, machine learning is great, but when you talk, to people about what's machine learning in real life, well, data scientists will tell you that data preparation is most of the work. And one of the reasons is that it's not automated. So it's basically a bunch of trial and error. And data scientists actually don't like this. They complain a lot about this. There's a common joke that says that in data science, data preparation is 80% of the work, and complaining about data preparation is 20% of the work. So data scientists prefer machine learning because it's more general. It can more be reused. So that's the first thing. And another thing is that data science, and in particular data preparation, needs a form of interactive exploration and iteration. It's really just hard. This part is just really hard to automate. And so that's the kind of story you get when you talk to data scientists. And then when you talk to people who are more production engineers, well, they complain about the code of data scientists. They say it's of not great quality because they can't put it in production. And if we look at, why there's this problem, well, one of the reasons is that the code of data scientists just tends to live in notebooks or in other kind of UIs like, VS Code that I'll be using today. That's good for interactive exploration, but not really production-like behavior. And one of the problems that, putting in production faces is that this kind of interactive work tends not to lead to a clean predictor. So machine learning is about prediction. So a clean predictor that goes from the database, from the raw data to the prediction. So that's kind of the scene. And if we take a step back and we look at the tools we have in the Python ecosystem, well, so I often like to brag about the fact that scikit-learn has a large number of downloads, typically 3 million downloads a day. But it's really interesting to look at pandas, which is used for data preparation in data wrangling at large. And pandas is much, much more downloads, so 10 million downloads a day. So, that kind of gives you the relative importance of the two problems. So we're going to be talking about machine learning today, and really to give a, machine learning in a nutshell. Well, the way it works for those who have never done it is that we fit models on trained data. And what those models do is that they learn to link a data set X that's a multi-dimensional data set. So typically, 2D matrix of numbers. They learn to link this data to Y, which is the output variable, the target that you try to predict. So X is typically number of samples, number of times you've observed a phenomena, an individual, times number of features, number of attributes that describes the individuals, and Y is what you're trying to predict. And so we do this on trained data, and once we've done this, we can take test data where we only have X test, we don't have Y test, and the model can predict. And ideally, the prediction is good. And an important point, and I'll come back to this, is that prediction error should always be measured on data that has never been seen during fit. If it's measured on data that has already been seen during fit, it doesn't qualify any form of generalization. It can just be memorization. Okay, with this, let me turn to a bit of Python code, and let me walk you through a typical data science pipeline. And so, we have data here. It's data on employees' salary. This is real data. So you can see here that we have a data frame with different features that describe individuals, and there is one column that's the salary. And that's the column that we're going to try to predict. So what we do is that we're going to retrieve that column, the salary column, and we're going to drop it from the data frame because we're going to isolate X and Y. Then what we're going to do is that we're going to use scikit-learn to split the data between trained data and test data. And we split, both the data frame and the target. And then we're going to import a predictor of regressor from scikit-learn. And here you can see how scikit-learn works. And we have a random forest regressor. It's a model that can fit. So by fitting, it learns to predict Y from X, here df. And so I give the fit method, I give it df train and Y train. Okay, now I'm just going to cheat a bit. I'm going to use a bit skrub because it's going to make my life much easier. Oh, darn. I had a value error. What does the value error tell me? It tells me that basically the model doesn't know how to convert some of those values to floats. And the reason is that machine learning more naturally works on numbers, and the data here is not numbers. So let's use Scrub to look at this data. And here I'm using the table report. The table report is basically a fancy data frame viewer, and it allows me to do things like inspection of the different columns. So for instance, in this department column, I have the distribution of the 10 most frequent values. I have 37 values, and I can see that the most frequent value is POL, which I believe stands for police, and you have 20% of the people employed by the police. And I can basically, explore this data. I can look at the statistics of the different columns, and I can see, for instance, that the gender column has 11 missing values, null values, that the department column has, as we've just seen, 37 values, and for instance, that the employee position title has 400 values. Okay, so what am I seeing here? I'm seeing that this data frame is a bit complex to work with. I'm going to have to turn this data into something that my machine learning model can manage. Okay, so then, I'm going to be doing exactly what I described just before. I'm going to be doing data preparation. So I'm going to use pandas to transform all these things to numbers. So for instance, I'm going to use toDateTime to transform the dates into things that make sense and that can easily be predicted by my model. So then I'm going to, extract the year, and then I'm going to also to drop the employee position title because it's too complex. I can't deal with it. I'm going here to convert all the columns, like the gender column, to what we call dummy encoding or one-hot encoding. It's basically coding with ones and zeros the categories. So I do this. Why do I not have get dummies? See, that's the fun of live coding. I probably had forgotten to run a cell, as always. Okay, and okay, so I've done, all this code to transform the data. Now I have xtrain. I've transformed my data frame into a numerical matrix, and I can fit the model. And it runs, and here it ran. And now I need to apply this model to new data. And so basically now I need to reapply those transformations to the test data. So I need to redo all the same things. And so I redo everything, and then I can fit this. Bang, it doesn't work. What's the problem? Well, it's telling me that it has column names that it doesn't know. And to cut a long story short, the reason it has column names that it doesn't know is because the pandas get dummies has created different columns for the different categories. But I had a different set of categories in my train set and in my test set. So there are columns that don't correspond. So the model doesn't know what to do about this. And so the problem that we're facing here is that we've transformed the test data and the train data independently. And so we need to transform them jointly, but we don't have the test data at fit time. So for this, we can use scikit-learn, and scikit-learn has what we call a one-hot encoder that basically does the dummy encoding by learning the categories at train time and applying them at test time. Okay, so now we do this, and we've retransformed our train data, and we can then apply the same transformation. It's the transformation I have here. Here we fit transform, and here we transform it. We can apply the same transformation at test time, okay? So now, we apply the same transformation, and now we can predict, and once we've predict, we can compute, for instance, an error rate. Okay, so you've seen the problem. That's a lot of work. And for every single transformation I do, I'm going to have to be very careful to learn a transformation on the train data and to apply the same transformation in the test data. And so I'm getting basically all my pandas code, I'm going to have to write it very, very carefully. Sometimes I'm going to have to separate fit and transform. It's just tedious. Okay, so we can do, so scikit-learn gives us tools to do this. It gives us the column transformer. The column transformer that we're going to create here will basically route different transformers to the different columns. It's going to route a one-hot encoder to the columns that we tell it here, to all those columns. It's going to route, this function transformer where I have I'm creating a function using lambda functions that will transform the different columns to date time and retrieve the year. And I'm going to apply it to the dates. I'm going to drop a bunch of columns. So, this basically big definition tells me how to do my pre-processing pipeline. And then I'm going to pipeline it with my random forest transformer. And then I can basically run all this, and then I can fit the pipeline to the raw data and predict. Okay? And having done this, what I just showed you is that this pipeline is just the whole pre-processing and can then just apply the transformer. I don't know about you, but I personally find this tedious. And to be honest, even though I'm using GitHub Copilot, I struggled a bit to write this, even though I know the package quite well. Okay, so the nice thing about this, by the way, is that now we can do things like cross-validation. So cross-validation means I'm splitting my data many times, and I'm measuring the error on the test set many times. So it's here we do this 5 times. And here, by the way, this is an argument to do parallel computing. So here are the numbers I get. I can do things like hyperparameter tuning. So I'm going to tune a parameter called max depth of the random forest transformer. And so here what I'm doing is I'm choosing the best one across those 3 values. And then hopefully it's going to give me a better learner. Okay, so that's the benefit of doing a pipeline. I can do cross-validation, I can do hyperparameter tuning. So I've shown you how to do this with pure scikit-learn, and it's still running. It often gets computationally expensive. Okay, now while it's running, I just want to show you how to do the same exact pipeline. Well, not the same exact pipeline, actually. It's a slightly different pipeline, but the same kind of idea with a scrub. By the way, this is run, and now with hyperparameter tuning, well, I didn't really get any benefit. So same idea, same pipeline, but here I'm going to be using the table vectorizer. And the table vectorizer is what we call a transformer, so something that can transform data. So it learns how to transform data at fit time, and it applies the transformation, the same transformation at test time. And so I'm going to, apply this table vectorizer in a pipeline directly with the random forest regressor. And then this thing can be just applied to data frames, because what the table vectorizer did is it transformed my data frames, my complex data frame that I showed you, it transformed it to a numerical matrix, to vectors of numbers. And so really, so here we have a visualization, and you can see, what it did. And it did the similar kind of things that I was doing before. It did datetime encoding, except this time I'm not using, crazy lambdas to do my datetime encoding. It passed the numerical through. The low cardinality categorical features, it used the one-hot encoding as before. The high cardinality one, it used something more sophisticated that I'll mention. And then it, because it's a pipeline, it's feeding this to random forest regressing. So basically, my table vectorizer did all the hard work that I was doing before for me. And as you can see, then, I can do all the nice things that I was doing before. So I hope I've convinced you that, for preparing one data table, it was much easier to do it with a table vectorizer, with a scrub table vectorizer. But that was just an introduction. Now I realize I have too much material, so I'll skip. I had a second Python file that was kind of showing you the details of the table vectorizer, showing you how it can, vary the transformations. It's based on a heuristic, basically. It applies different transformations to different columns with a bunch of good heuristics. But I'm going to skip this. Well, you know what? I'm going to skip this, and if we have time, I'm going to come back, but I want to talk about something really exciting. So the table vectorizer is incredibly useful. I just can't work these days without the table vectorizer. But, let me show you something. Let me show you science fiction. let me show you something that we've been working on over those last month that is not merged yet. There's a pull request for this. So I'm taking risks. This is a work in progress pull request, but I want to show you something super exciting. So right now I've shown you how if I'm given one table, I can basically, transform it in good ways to prepare it for machine learning. But let me show you a more complex setting that happens quite often and for which I know no good answer currently. So this is a setting where we're interested in credit fraud. And so we're given a first table, which gives us IDs of transactions and a fraud flag, okay? And so we can see that the fraud flag is very imbalanced. We have only a small fraction, only 1% of the transactions that are frauds, okay? And so I have a second table where I have products, and those are the transactions, and I have a basket ID, and then I have a bunch of different things associated to it. And then the challenge that I have here is that this basket ID repeats across the different lines, right? So basically, what I have is that I have you can see it here. For instance, I have one basket where the transaction has both bedroom furniture and outdoor furniture. Okay. And so what I'm going to need to do is basically to merge those two tables, to merge the table with a basket ID that tells me whether there was a fraud or not, and the table with the items in the basket. And so if you know data wrangling, if you know pandas, this is a quite classic problem. We're going to have to do an aggregation on the product table and a join or a merge on the other one. So just to give you an idea, the kind of baskets that we have look like this. This is a basket with 3 items. It's got, computers, a warranty, a fulfillment charge. And okay, so we're going to need to do an aggregation here. And here I'm going to do something that's not conventional, is I'm going to vectorize this table. Okay? So I'm vectorizing this table. And so what the table vectorization here is going to embed the strings using semantic models for string embedding. It's going to embed the strings, and it's going to transform this into a fully numerical table, which is going to make my life much easier. And once I've vectorized this table, it becomes much easier to aggregate it. So I'm going to aggregate it along the basket ID dimension by taking the mean. And so now that's much easier. And now what I can do is that I can merge it in. Now that I've aggregated it, I can merge it in the basket table. Okay. So now I've merged my two tables, and now I'm back to the previous situation, and I can do machine learning on this. I have my X. I can extract my X and my Y's, and I can do machine learning. And so here I'm just going to use an extra tree classifier because it's fast. Because this example is a bit lengthy, and then I can do, as before, I can do a cross validation, and you can see that I've managed to predict reasonably well. 1 is perfect prediction, and 0.5 is chance. Okay, but we have a problem. If new data comes in, I need to reapply all the transformations as before, but now it's harder. I need to apply those transformations across multiple tables, so it's a much harder problem. And I'm going to show you a solution we're still working on. It's a pull request, but we think it's almost ready. And the solution is actually very close to what I've showed you before. We're not going to change a lot, but what we're going to do is that we're going to start declaring those source variables as variables. So here I'm declaring the product variable, and I'm calling it product. Where am I? I got lost. Yeah, I'm declaring the product variable, and I'm declaring the basket variable. And the basket variable, as you can see here, I'm extracting the ID and I'm marking it as X, the thing I'm going to try to predict from. And I'm extracting the fraud flag and I'm marking it as Y, my prediction target. And then I'm going to do basically the same thing that I did before. So I'm going to vectorize and then merge. But I'm going to do it with a very slightly different API. I'm going to the product table. I'm going to apply the vectorizer on all the columns but the basket ID. And on the resulting vectorized product, I'm going to aggregate. So this is the same syntax as before. I'm going to aggregate. And then I'm taking the basket ID that I had here, and I'm merging the aggregate product. So I'm doing the same thing as before, and I'm dropping the ID and the basket ID, which were just important to do the merges. And then I'm going to apply the extra tree classifier with a target, the fraud flag. And this is going to run, and I'm going to get a prediction. Okay, so I've done the same thing as before. But what's important? Okay, so I've gotten a prediction. It looks not very different from what I did before, but under the hood, there has been a graph of operations, a graph of computation that's been built, that's tracked everything that was done from the original data. So now that I have this, this graph of operations, I can apply it to new data. So here I'm loading new data. I'm loading new data. I'm retrieving my X variable. I'm retrieving my Y variable. I'm grabbing the predictor from the previous pipeline, and I'm calling predict. But now my predict method, unlike scikit-learn, this is not exactly a scikit-learn predictor. It takes a dictionary of variables, and those variables are the variables that I had declared earlier. So I'm basically reapplying my whole set of transformations, including the prediction. Okay. And now finally, I can evaluate my prediction. Now, what's the big deal? Once I have this, I can do all the goodies that I was doing before with scikit-learn, things like hyperparameter tuning. So here it's a slightly different syntax, and it's a better one, I like to say. I'm using a choose from function, and I'm telling, I'm saying, that in this step, in the string encoder, I want to vary the vectorizer argument, and I want to vary it between two different arguments, TF, IDF, and hashing. You may not know what that is, but that's not really important. And then I'm going to apply it, yada yada yada. I do the same thing, but here this is the same exact thing as before. But here I'm doing a grid search, and what the grid search will do is it's going to try the two options, and it's going to pick the best one. And so this is why it's taking forever. This is going to take a little while. It's why it's taking forever, because it's doing cross-validation, it's doing multiple splits. It's doing cross-validation, and it's testing the two options, and it's testing the one that works best. And so once it's finished, we're going to see it's going to compare those two options. It's going to tell us the one that works best. And so it's running, and so I've got two more things I want to show you. I want to show you that I can do visualization that use basically the fact that I can track things across the pipeline to show you things that are happening. And I'm going to show you the compromises of hyperparameter selection. This is a very simple example because I wanted to not run too long. And I can also show you a full report actually while it's running. I'm going to show you the full report. So that's the full report. It's the enhanced version. We're still working on this in terms of UI. But what you can see is that you can inspect all the pipeline steps. And each time you can see, for instance, where it was defined and the value of the tables at this moment. Okay, so we're going to keep working on this to make it really helpful for debugging pipelines. Okay, so it's still running here. So maybe we will not know the answer of this. So I'm just gonna switch to my conclusion, my closing remarks. So what have I showed you? You know, I've showed you that to prepare one table, we have, you know, enhanced tools that basically do a bunch of really clever automatic choices that really help compared to manual preparation. And really the table vectorizer is central to this. That's a really robust part of Scrub. I can't live with it anymore. Without it anymore, sorry. And I've shown you for the more open problem, if we have an open-ended sequence of preparation, data preparation, well, I've shown you kind of a modern way of doing things where we're blending machine learning steps such as the vectorization in the middle of the pipeline. And so these machine learning steps, they can be used for vectorization, can be used for imputing missing values. The kind of paper, API that I'm showing is very versatile, but it's super standard. You know, it's look basically like pandas. And the reason it looks like pandas is it's wrapping the standard objects. Here we were wrapping pandas data frame, but we could be wrapping polars data frame. You can try it. Works with polars today. It can be applied to anything, and it's just tracking all the operations. I've shown you how it can be put in production because it creates a pipeline that I can then move in production and apply to new data simply by calling it with a dictionary. But every aspect of the pipeline is tunable as we're seeing, as it's still running. I've shown you the visual debugging. Long term, you know, what are the stakes? Well, we're going to keep making this better. We're going to, for instance, integrate subsampling to make this much faster. It will be great. And then we want to connect this directly to database. So if you're working on really large data, you can, using this kind of pipeline, you'll be just able to transform the data using the database engine. And I want to end by saying that Scrub is community driven. It's an open source project. You can come on GitHub, you can try it, you can help us out. And one of the way you can help us out is by using it and communicating if you like it. Thank you very much.
Thank you, Gaël, for those fantastic, or that sneak preview of a very interesting package and those fantastic comments. I want to open it up for any Q&A from our audience. Make sure that you use either the Q&A widget or the attendee chat in order to register your question. And while we do that, I also want to give our host panelists an opportunity to introduce themselves and to make themselves available to answer any of the questions that you might have of them. Joining us today, we have three host panelists from Brookhaven National Lab, Phil, Hiran, and Tom. Phil, would you like to briefly introduce yourself and tell us a little bit about the kinds of questions you would be happy to answer in today's session?
Yeah, absolutely. So I'm Phil Maffetone, coming in live from New Mexico. So if my Wi-Fi is spotty, I do apologize. My background is in machine learning and AI for scientific experiments. So I've worked in the private sector and now in the government sector on these kinds of problems. So really happy to answer any questions on sort of the applied ML space and trying to scale ML. So a lot of the work that I'm doing now is trying to scale these things to more productionized instances.
So I take it, Phil, you're the person that the scientist goes to when they say, I need to add AI ML somewhere in my grant proposal. Can you tell me what I can throw in there?
Oh, I am 5% on a million proposals.
Fantastic. Also joining us from BNL, we have Hiran. Hiran, would you like to briefly introduce yourself and tell us about the kinds of questions you can help people answer?
Yeah, so I'm Hiran. At BNL, I work in data analysis and workflow integration, more emphasis on workflow integration side. So the AI and ML stuff that I've done are mostly the projects that I've done for fun. And I'm kind of getting into applying more for this type of techniques for the stuff that I do at work. But I'm generally very interested in this site. Maybe I may have more questions than maybe answers, but yeah.
Fantastic. And finally, from BNL, we have Tom Caswell joining us. Tom, the same question to you if you'd like to introduce yourself and tell us the kinds of questions you'd be happy to help us talk about today.
Hi, so I'm Tom Gazel. I'm the deputy group leader in the data acquisition detector group at Brookhaven, or at NSLS2. I'm also the current project lead for Matplotlib. I guess I'm happy to take questions about data acquisition processes or plotting or managing large-scale open source projects.
Fantastic. Of course, that managing of large-scale open source projects is a very tricky thing, and I'm sure, Gaël, you have some comments on that as well. Now, of course, I do want to invite all of our attendees to submit their questions either via Q&A. We can also pull you up into the discussion if you raise your hand, or via the chat. If we don't have anybody out the gate with any questions, I do have a somewhat off-topic question, but only off-topic in that it's not quite related to what Gaël shared with us, but it's something that seems to come up quite a bit in my life. Am I the only one who feels like LLMs have sucked all the air out of the room talking about anything related to machine learning? And are there effective ways to go back to people and say, no, 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 there's traditional techniques that actually work, that we know work. Maybe let's start with those before we jump for the new shiny thing. Gaël, Phil, Tom, Hiran, any thoughts on that?
Sure, I have plenty of thoughts on that.
We'd love to hear them.
Well, I mean, of course, LLMs are sucking their, all the attention, and there are many reasons for this. One of them is they're amazing. I mean, I was using GitHub Copilot to code those slides, and it was a lot of fun. And we don't want to dismiss them in any way. It's just that there are a different set of problems, and they answer a certain set of problems. Now, I think the best way to get people to stop talking about LLMs or to stop talking only about LLMs is just to let them get tired. So no, seriously, I mean, and also to show the bell that goes with it, because if they try to solve every single problem, you can even do tabular learning with LLMs, but putting this in production is simply not going to work. And then you go back to, well, we have data, and this data is not the kind of things that LLM is designed for. So the important thing is, so the conversation has been one thing that's really bad about this conversation. God, you hit me on a topic that's really important to me. It's another aspect of my life also. I do government advising and things like this. And one of the reasons why we're having this conversation is because they're great promises. People are talking about artificial general intelligence. I don't think this is warranted, but people are getting excited because it's a really cool technology. And with every really cool technology in history has come a bubble, a technological bubble. So technological bubbles most of them are not built on nothing. They're built on something that is seen as too important. But when there is a bubble, what do people do? Well, they try to make it bigger, because the bigger you make the bubble, the bigger everybody who is in this bubble gets. And so the current thing is that everybody is telling you that LLMs are going to change everything. They're so intelligent that they're dangerous and they might go after us tomorrow. And for this reason, they need more money. I need more money, because if I get there first, I'm going to be the most powerful person in this room and on this planet. But also, you also need to give me money to make sure that it's safe. So, that is the way you need to think about this.
So
how do we fight this? Once again, pragmatic.
Very good. Now, I'd like to open up for any comments from our other host panelists, Phil, Hiran, Tom, on that topic, or returning to our prepared remarks, our topic of data wrangling for tabular machine learning.
I will gladly kick LMs while they're down, and then offer a helping hand to give them a role in our society. I think I agree broadly with what I was saying. But one of the really, I think, potent spaces for active research and also sort of productionization of these tools is in tool use, right? I mean, I was talking a little bit about how he prepared these slides, right? He's still there at the interface of, I talk to my intern LLM gives me some decent advice. I type backspace a few times after tab complete, and then I fix up what I was working on to prepare these slides. A really potent space where I think we're close is to say, my LLM knows about computational resources that's available to it. It's using tools like Scrub that are capable of doing repeatable assembly or repeatable data wrangling, and feeding that to scikit-learn and giving me interpretable and actionable responses from queries or from active work. And I think if you look at the ChatGPT UI right now, you can break it pretty easily because it tries to make matplotlib plots that don't always compile. But now it will expose that matplotlib code that fails, and you can steal that and then go actually make the image that you were after, especially when you're trying to make images for publications that are useful, that you need like in vectorized quality. So we're getting closer to that kind of a capacity, but that's a space where, you know, when you have effective tool use that knows about its resources, you can actually do things that are interpretable using sort of our old school probabilistic and statistical techniques.
Where I were here. Sorry, Iran, you wanted to say something? Go ahead.
Yes, I was just gonna say, so the LLMs, what we have today is kind of already an approximation of AGI, but we are kind of not realizing that because of our general, the other side of intelligence. I think a lot of, like, for example, right, a lot of companies, what they're doing with LLMs is that they have this chatbot that is going to solve all the customer queries and stuff like that. And it has access to business data, and they're just hoping that that'll solve all of the problems for the customers and cut costs for them. So that's the reason for the excitement for LLMs, at least from the corporate side, mostly. But I think the real application of LLMs is that, so we have this linguistic-based model for reasoning that doesn't necessarily have to face the customers. And so it's not just a chatbot, you can use it for reasoning. And I think there's a lot of applications in that, rather than just like using it as a chatbot that just faces the user. So in that, I don't think a lot of people have explored that a lot yet. And I think there's a lot of potential, but the one point about the generality is that it's a general solution for a lot of things already, but it's not the best solution for a lot of things already as well. So I think that's the key point that a lot of people are missing also, that we have already the pretty good, pretty solid machine learning techniques and tools that have already solved other problems really well, but we're just trying to gain like a one general solution that fits everything. That's where the problem is.
Well, maybe I can comment on the reasoning. Now, I'm taking another hat, which is my AI researcher hat, not only my coder hat. And we need to be quite careful about what we say here. I mean, the terms are getting quite mixy. The reasoning engines that we're seeing, the more like a vanilla LLM by itself isn't really good at reasoning. Vanilla, I mean, but then what I think what I've been learning in the last couple of years is that a lot of intelligence is memorization. Much more than what I thought. It's basically memorization and cheap interpolation, which solves a lot of problems. But your vanilla LLM is not really good at reasoning. It's easy to think it is because we as human beings basically always ask the same questions. And so when we ask a question to an LLM, we get an answer that looks clever, but that's because that question was already asked before. By the way, try playing tic-tac-toe on the LLMs. You can try asking a crazy math question. It does really good. Then play tic-tac-toe on a standard LLM. It's disastrous. And tic-tac-toe, come on, that's now there are indeed more powerful reasoning engines that are basically, I don't want to get too much into details, but basically it's no longer really an LLM. It's an interaction between an LLM and something that breaks down the problem into sub-problems. And now this works. And if you enable those reasoning engines in the chatbots, then they start being good at tic-tac-toe. But without this, they're not good at tic-tac-toe. But then they start, taking 30 seconds to reply because they need to do many steps. So, we've just designed a really, really, really powerful engine that takes 30 seconds to play tic-tac-toe. So, on this, once again, I'll challenge a bit the narrative. It's not, just Gen AI solves it.
So, James, I would ask a question that's going to move us a little away from LLMs. So a trend that I've noticed recently, and Scrub shows this, the move away from strictly imperative programming models to building up computation graphs, right? So Scrub does this. We're looking at something similar, Matplotlib, and some speculative work, Dask, polars. So is there a shift coming in the way we program to be all computation graph instead of imperative, and what does this mean for Python?
Well, so scikit-learn was designed with the idea of trying to hide declarative in an imperative way. You know, this thing where you create an object by giving it all its argument is a query in functional programming, and then fit and transform. So it was really designed like this. And the reason it was designed like this is declarative programming has been there forever. You know, SQL is declarative programming, and it's really good for many things, but it's really bad for the brain. People hate it. It's just, I've heard this story. You know, I've sat with computer scientists for decades, and they always tell me that declarative programming is better, and then the minute you come and talk to users, it just doesn't work. So we've been going back and forth for decades, and the challenge is to find the kind of right UX, but UX for a library to make this work. To me, that's it.
And that was actually something that I wrote down in my notes as you were talking, is like, oh, this feels like Dask for data wrangling. And to that extent, right, where does this project go in terms of the optimizations that Dask starts to give you in terms of distributed programming and execution?
Well, it doesn't go anywhere because I mean that's not really our goal. I mean, the project actually doesn't know much about the computation engine, and that's not what we want to do. I mean, if we start knowing too much about the computation engine, then we're going to do things like reinvent Dask or reinvent all these things. In theory, I mean, I haven't tried it, but in theory, you could literally put a Dask thing in it. I mean, the only thing it's doing is it's recording what's happening. So you could totally put a Dask object in it. We've tried it with lazy polars, which also surprisingly build a computational graph. We want to use it with things like IBIS, and hey, we're back to this, declarative, because what IBIS does is actually generates a SQL, and SQL is declarative. So it's always the same thing. So computation graphs. So we don't want to go in the direction of a Dask. We may complement it, but we're certainly not going to re-implement any kind of this parallel computing, any kind of this scheduling. That's not what we do.
Maybe this is an incorrect assumption, but my thought always of what scikit-learn was supposed to be is it's an ad hoc tail end human-driven tool. So you're sitting at your Jupyter notebook, you're just typing lines to do some scikit-learn analysis. If it's slow, well, it's just got to be fast enough to work on about the size of a pandas data frame. And then once you've discovered something very interesting, if you need to put this into production, then you'll double down on going back to the original literature, figuring out how to re-implement this in maybe C or C++ or Zig or whatever, and find the places where the scikit-learn API does not allow for optimizations you need, and actually with custom data structures or whatnot, build that in. And there's a little bit of a fiction there because people, of course, will always push a convenient tool further than it needs to go. But is that not the model by which Scrub and scikit-learn were designed to be used?
I wouldn't say these days. What I've learned, in these long years of doing this, is that it's hard to implement well a numerical algorithm. No surprise. That few people know how to do it. Now, maybe in the very rich, areas, typically finance, you get some people recoding, but less and less. It's just too costly. So there's less and less of recoding of the numerical algorithms. So people might move to other tools, to quote unquote more powerful tools. But I mean, I know even, really large companies who have in-house code bases who are talking to us to say, they want to get rid of the in-house code bases because maintaining them long term is too costly. So, there's a question, of course, which is how, can we work on scikit-learn to make it better? We're doing this, but I can't say we're a small team, but we're the size of the team compared to the number of algorithm is challenging. But I don't really see recoding very likely. Maybe what you're going to do is that you're going to find out the bottleneck, and maybe you could recode it.
So then from that perspective, if you don't have an imperative API, then are you not risking that when people actually need to use this at larger scale than whatever they can fit into a Jupyter notebook for some prototyping, they no longer have the aspects across which they want to actually perform optimizations? Like you see this with matplotlib. Any kind of streaming data is basically impossible to do. The API does not allow you to do that.
So I don't know about, so streaming is pushing this. We don't have streaming in mind. It might work, but I think we need special primitives because even from a statistical perspective, you need to do things differently. But a very large data, I do have the hope. So you wouldn't work the dream is the following. You've prototyped. I mentioned in the closing remarks. I mentioned subsampling. So you've prototyped on data that's actually smaller than the one you have on your laptop. I like working on my laptop. This was done on my laptop. I crashed it at the end, by the way. But once you've prototyped it, in an ideal world, and maybe we'll be there at some point, not too far, you can push this to servers. And on the servers, you've got bigger infrastructure, maybe distributed computing, things like this, but you're pushing your computation graph. So you've used, your interactive programming to design this computation graph, and then you're pushing it to bigger infrastructure. That's what we're hoping to achieve. And we're hoping to achieve this also by ideally sitting on computation engine like IBIS, like Dask, like other ones. We're not replacing them.
Now we do have an audience question. I have allowed the audience member, if they choose to unmute themselves, to ask directly. I'll give them a moment to do that. If not, I'll provide the question. The question is there any interest in semi-structured data, JSON with incomplete schema, semi-formatted log files, or is the focus for Scrub on tabular, multiple table-based data? Of course, our attendee knows that that's their question, and they can jump in if they need to provide some additional clarifying detail.
Well, that's a good question. I hadn't thought about this in terms of Scrub. So I'm also running research projects that are more open-ended and more wild, where we're developing tools that can work on one day this kind of data. I'd like to say, all right, I'd like to say short-term, no, long-term, let's see, because some of the problems of this data isn't too far from some of the things we've seen here.
Fantastic. And of course, if there's a follow-up from our attendee, we'll give them an opportunity. For the rest of our attendees, if you'd like to add your own question, either in the chat or in the Q&A widget, we'd love to hear it. Otherwise, we're just going to go back to complaining about LLMs. As I said, they suck the air out of the room for everything.
There's something I wanted to add, something I wanted to add on the LLM thing about coding. So I see kind of the narrative that because we have, Copilot, we're no longer going to need libraries like Scrub that make it easier to code. And I think that's maybe everybody agrees here, but I think it's a very dangerous fallacy because the problem of coding is not writing the lines of code. It's reading them to know what they do. And so we're going to get, crazy complexity because people are going to generate, crazy pipelines that nobody understands. And on top of this, it's true also for the LLMs because yes, they reason, but not much. So we do need these, these clean libraries that have the right abstractions, even with, LLM generators.
You ever watch James Powell try and live code pandas wrangling? You have to play it at half speed for a normal human to understand all of the chained queries. And I don't think ChatGPT would keep up.
It can be a little bit intense. Now we are reaching the time that we have allotted for this session. I do want to open up for any final thoughts, questions, or comments from our audience. If not, let's take some final thoughts or comments from our host panelists. We'll start with Tom. Tom?
So I'll add a funny use I found for ChatGPT is we were having a discussion on Matplotlib of what our policy should be about users using ChatGPT to respond to issues or open pull requests. And I asked ChatGPT why it should not be used for this purpose, and it gave me a verbose but reasonable answer.
Very good. Use the tool against itself. Fantastic for that comment, Tom. Hiran, any final thoughts or comments before we adjourn?
Yeah, so final comment, I'm like really excited to give Scrub a try. And going back to LLMs, I'll just say like one use case that I really like is to ask LLM like to describe things in weird perspectives, like describe a war from the perspective of weather or some stuff like that. Challenging, but also sometimes very insightful as well.
Very good. Final thoughts or comments, Phil?
Yeah, I'm quite excited to share Scrub with some folks at the old company I used to work at to see if they want to grab on. I do have one follow-up question to that point, right? So the old ML team I was on, it was 3 people doing ML at the start, 10 people doing data science, and 15 people doing engineering, which is, it kind of goes back to the point of how much work each of those actually takes. So how mature is the API, right? If I go share this with people and drop it on them, what should I tell them to say, hey, look into this, start putting it into your production code bases now, or hey, start playing where this makes good use for you, but keep in mind the API is going to be fast moving.
So the table vectorizer is really settling down. Actually, we just decided that we were going to do a change. We're learning. The problem is we're really learning. We're learning to do things better. That second thing that I presented, that's still a pull request. So,
Right.
but I mean we've been playing with this for a while. We've gotten feedback. We're starting to be happy, but it's still a pull request.
Fantastic. And we will give Gaël the final word for today's session. Thank you so much for joining us and for a sneak preview at a very exciting tool. Gaël, the final thought?
Final thought, open source is crucial. Open source is crucial because as we work together, we make better tools. So let's keep doing it.
Fantastic. Thank you all for joining us, and we'll see you all next month.
Thank you.